Hello, everybody. Welcome to this session. In this session, we want to talk about introduction to Candence software. Candence is a software that you can use to simulate a very simple electrical and electronic circuits to a very advanced level designing a integrated circuit IC chip. Let me share the slides for this session. In the second half of this session, well, we will log into the Cadence software and I will show you how to simulate a very simple electrical engineering circuit. But in the first half, we'll work and review what we were discussing in the previous sessions about the NMOS transistors. And we will plot the IV characteristics of an NMOS transistor. By IV characteristics, I mean I as a current and V as a voltage. We will plot how to plot IV characteristic of an NMOS transistor. This is the structure of a MOSFET device. By MOSFET, MOS, we mean metal oxide semiconductor. Um, when you say semiconductor, it means the substrate that your electronic or electrical circuits, other terminals, other components are built on that substrate. That substrate should be semiconductor. A very standard substrate that all our chips, ICs are built on would be silicon. So this silicon the substrate would be P substrate. To form the MOSFET transistor inside that P substrate, the silicon substrate, we will diffuse 2N plus area to form the source terminal and drain terminal. Between these two N plus, we will add oxide as a dielectric, and because our substrate is silicon, this oxide would be silicon oxide or SiO2. On top of that SiO2, there would be there would be a metal layer to have a connection for a gate terminal of the transistor. So our transistor would have eventually 4 terminals: drain, gate, source, and a substrate, which will be called as a bulk or body of the substrate. This is the cross sections of the transistor, NMOS transistor, and this is the symbol or schematic of this NMOS transistor. Again, you will see those 4 terminals: drain, gate, source, and bulk or body of the transistor. And the source terminal in the schematic always we show it with that arrow. Now we want to talk about the IV characteristics of this NMOS transistor. Imagine all 4 terminals of the transistor are grounded, no voltage. And we gradually put voltage on the gate terminal, slowly increase the voltage on the gate terminal. What happens? Because there would be a positive voltage, positive electrical potential on the gate, the negative ions from the silicon substrate comes to this gate terminal. And we will introduce a voltage as a threshold voltage of this transistor, which is threshold voltage VTH, depends on the technology that we use, is typically around 0.4, 0.5 volt. When the VG is less than threshold voltage, less than that 0.5 volt, there would be only the negative ions under this gate channel of the transistor. But when the threshold voltage is great, sorry, the VGS, the voltage between gate and source. Source is grounded, so the voltage of the gate is greater than the threshold voltage. The electrons will be absorbed, will be collected, and will be formed a layer between these two N plus under the transistor's gate channel. And basic electrical engineering. Whenever we have electrons, we will, if we put a little voltage in one side of the uh, electron, that electron layer, the electron moves. Well, with the mobility of the electron, you would have a DC current flowing. So when we VGS, the voltage between a gate and source terminals are less than threshold voltage, there would be no electrons and no mobility of the electrons and no DC current. So we say the transistor is off, is cut off. But when VGS is greater than threshold voltage, you will have that layer of the electrons and the transistor is on. When the VG is higher than threshold voltage, but still the gate and source, sorry, the source and drain terminal are grounded, we say the equal source and drain voltages. This electron layer would be like symmetrical between the drain and source. But when you have an unequal source and drain voltage, it means keep the source grounded, but slowly increase the drain voltage, put the potential on the drain. You will see that under the channel of the transistor, the electrons closer to this high potential, the positive potential, will be absorbed in the N plus area, and the density or intensity of the electrons closer to the source, which is grounded, would be higher. This distance between these two N plus will be called as a L, or length of the channel of these transistors. And the width, this distance would be width of the channel, width of the transistors. The L is a fixed number, depends on the technology that we use. If we're using 180 nanometer CMOS technology, that L is 180 nanometer or 0.18 micrometer. If we use 90 nanometer technology, that L is 90 nanometer. Or the newer technology would be like 45 nanometer or 22 nanometer, or these days in the news, you might hear that they're working on the 7 nanometer or 5 nanometer technology, which means the length of the channel would be like 5 nanometer or 7 nanometer. But the width of the transistor depends on us as a designer. We can design that width of the channel can be like 5 micrometer, 10 micrometer, 100 micrometer, or in some application even millimeter width for the transistor. Again, continues to the IV characteristic of the NMOS transistor. So we said if the VGS is less than threshold voltage, your transistor, there would be no electrons mobility, your transistor is cut off. But when the transistor is on, the VGS is higher than threshold voltage. You have two modes for your transistor to operate. This is the I versus V characteristic. By I, we mean the current that flows from drain to source. Imagine your source is grounded. And by VDS, again, we mean the voltage between drain and source. And if the source is grounded, would be the VD. Slowly, you increase the VDS, the drain voltage. And still, when VDS is less than VGS minus threshold voltage, means you are operating, your transistor is operating in this area. It is called triad region. Or if you look at these curves, these plots, you would see they are almost linear, roughly linear. And the triad region, the other name of it is a linear region. If you keep increasing the VDS and your VDS is higher than VGS minus threshold voltage, your transistor would be in this area. It's called saturation region. And as you see, the ID, the current of the transistor, would be independent of the VDS. Means if imagine this point and this point, the VDS is higher, increasing, but the current of the uh, transistor is constant, is saturated. So this is called saturation region. Depends on the application that you want to use your NMOS transistor in. You can design, as a designer, you can design and you can use one of these two triode region or saturation region. For example, if you want to use your NMOS as a switch, means when you put the voltage on your gate, any signal that you have in a drain goes to the source. Means your transistor or your switch is on if you put the voltage on a gate. But when you remove the voltage and no voltage on a gate, means your channel, those electron mobility, no electron, no channel between drain and source, and any signal that you have on a drain would not go to source. So your transistor would be off. So if you put the voltage on a gate, switch is on. If you remove the voltage on a gate, the switch is off. If you want to, your transistor operates as a switch, it is better to design your DC bias condition of the transistors in this area, in triad region. But if you want to use your transistor as an amplifier, you have to design your transistor on a saturation region. We will talk about that in the future sessions. But as a summary, now we want to show you some equations for what we discussed about the current of this NMOS transistor, the ID, based on the VDS, VGS, and VTH, the threshold voltage. The ID, when the VGS is less than threshold voltage, as we explained, when VGS is less than threshold voltage, there is no electron and there's no channel between drain and source, and your transistor is cut off, or the current is zero. But when VGS is higher than threshold voltage, your transistor is on, and you have two modes. If the VDS is less than VGS minus threshold voltage, your transistor is operating on a triad region, and this would be your ID, the current of the transistor. K is a parameter, depends on the technology. I will explain later. VGS minus threshold voltage multiplied by VDS minus VDS squared over 2. This would be the current of the transistor when it operates in the triad or linear region. But if you keep increasing the VDS and your transistor is in the saturation region, means the VDS is higher than VGS minus threshold voltage, your current is K over 2 VGS minus threshold voltage S squared. And as you see in this equation, your current is independent of the VDS. There is no VDS in this equation. So it means your ID, your current, versus VDS is fixed. By increasing the VDS, your current is constant. But still, your current depends on the VGS minus VTH. But what is the K? K is called process transconductance parameter. Depends on the technology. Mu n, C oxide, W over L. W and L. W, we said, is the channel width, and the L is the channel length. The length of the channel, I said, fixed number, depends on the technology that we use. 180 micrometer, 180 nanometer CMOS technology. The channel length is 180 nanometer, 0.18 micrometer. But the W is the width of this transistor, this channel, which depends on us. As a designer, we can change this width. Mu n is mobility of the electrons. As I explained, this electron that form the layer under the channel of the transistor, the mobility of that electron, again, depends on the technology that we use. That has a number, a coefficient, and C oxide capacitance per unit area. As I explained, the oxide, which formed that dielectric under the gate, because of the dielectric and the metal, you would have a parasitic capacitance here. It is called, is defined by C oxide. And because this oxide is a silicon, that coefficient is based on the silicon substrate. And by knowing these numbers, we will have the K as a coefficient, and by the other, depends on the DC bias that our transistor is biased in that condition, we will know if our transistor is cut off, is in the triode or linear region or in the saturation. Uh, just as a summary, before we go log into the cadence and we go to the cadence, and the goal of the cadence is to plot this IV characteristic of an NMOS. This is the slide that we're gonna, when we go to the cadence again, we're gonna come back and forth. This is the simplest circuit that we want to do. The transistor, 4-terminal transistors, transistor. We will put the voltage, DC voltage as a VG on a gate and VD on a drain, and your source is grounded. And we will plot the ID current of the transistor versus VDS. And we will first try to plot one of these plot of the with one VGS, and then we will try to what happens if we increase the VGS. Now let me go to the cadence. This is the schematic area of the cadence that we can build our own circuit. During this tutorial, I will tell you some short keys on your keyboard that you can use to draw your schematic and then run your circuit. First of all, use keyword I on your keyboard, and it gives you the instance to add the component. Then do the browse. The technology that we want to use is a TSMC 18, means 0.18 micrometer or 180 nanometer. On the categories, we need a transistor, 4-terminal transistor. On an RF device, on the MOSFET, RF 40 means 4-terminal, and we choose the first one. RF NMOS 2 volts means the maximum voltage that you can put on each terminal of this transistor is 2 volt. On the symbol, you choose this transistor. This is the drain of the transistor. This is the gate. This is the bulk, and the source. You see it's show with that arrow. We also need again, you click on the I, browse, and you come here on the analog lead. On the sources, on the global, the first one gives you a GND, which is the ground that we need to connect to complete our circuit. Again, I, browse, and on the independent, we need a DC source. Look for VDS. Again, symbol, and we need 2 sources, one for VG and one for VD. So we are almost completing our circuit. We have the transistor, we have grounds, and we have VG, and we have VD. Now the wire connections. On your keyboard, use the shortcut W for wire and connect the gate to the source, gate to that DC source. The source terminal would be grounded. The drain would be connected to this source. And we also need two other grounds we copy here with the short key C, and we complete our circuit. Now, click on this DC source, and with the short key Q, it shows you the properties. On the DC voltage, you can put whatever voltage that you want, 0.5 volt, 1 volt, 2 volt, whatever voltage that you want. But you also can put the parameters. We first put VG. And on this one, we will write VD. We define this as a parameter. And on the transistor side, again, just click and press Q. The length of the channel, because the technology we use is 118 nanometer or 0.18 micrometer. And the width, it shows the total width is 15 micrometer. If you want, you can increase or decrease it, but we keep it as it is. So the width of the transistor is 15 micrometer and the length is 0.18 micrometer. So if you divide 15 over 0.18, you would get something around 83, 84, the ratio of W over L. Now we want to run this circuit. You go to launch, ADEL, and first brought the variables from the circuit. The rest of it was from my previous simulation, which I will delete them. So you should have only two VD and VG that we define, VD for the drain and VG for the gate. As a default, I put both on a 1 volt and 1 volt. Go to the analysis, choose. We want to do the DC analysis, choose a DC, and here do the save DC operating points. Means after doing the simulation, we want to save the results, and we want to see or plot the results. Let's plot. Every time you have to save. This button is the save button for the schematic check. We run with this green like play symbol, you run, your simulation finished, and you go to the results. Annotate DC node voltage. It'll show you the voltage of the nodes. And one more time, results, annotate the DC operating points. It gives us these numbers that we are looking for. So the gate voltage, we put 1 volt. The source is grounded 0. And one more we need to add is the bulk. The bulk also need to be grounded, the fourth terminal of the I run one more time. So the gate is 1 volt, source is 0, bulk is grounded, and the drain, again, 1 volt. In this scenario, your current that flows from drain to source or as an ID would be 2.5 milliamp. And VGS, the voltage between gate and source, would be 1 volt. The VDS, voltage between drain and source, again, 1 volt. And VTH is the threshold voltage. I said, depends on the technology that we use. It's 546 millivolt or 0.55 volt. 0.55 volt is for this technology, 180 nanometer technology. It can go a little higher and lower, but it's like around 0.55 volt for this. Now let's do go back to that um, slides. We said if VGS is less than threshold voltage is 0.5 volt. If we put VGS around like 0.2 or 0.3 or 0.1, what's gonna happen? We know theoretically that there would not be no electrons, and even we put the voltage on the gate and drain, because you don't have that channel, no electron mobility, you would not see no DC current. So let's put the VG less than that 0.5 volt. Let's put it, for example, 0.2. VG as a 0.2. Still, you have a voltage on the drain. Let's simulate. You see, VG is 0.2, VDD is 1 volt. Threshold voltage is still 0.54, but the current went to nanoamp. From 2.5 milliamp, it went not even microamp, it went to almost zero. It went to the nanoamp. So your channel is off, your transistor is cut off. So there would be, if the VG is less than threshold voltage, 0.2 versus 0.5, you would have no current. Now let's go back to the 1 volt, and the goal was to plot ID versus VD of the transistor for 1 VGS. Let's keep the VG as a 1 volt, and the VD we want to sweep from 0 volt to 2 volt. Go to this DC analysis, just double click. Here on the design variables, variable name, we want to vary the VD and automatic change it to linear from 0 volt to 2 volt with the step of, you can put 0.1 volt. Means 0, 0.1, 0.2, 0.3, 0.4, 0.5 up to 2 volt with the step of 0.1. We want to sweep the VD and see how the ID versus VDS shows. Again, you run the simulation, and you see it ran the simulation based on VD 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 1, 1.4, and up to 2 volts. Now again, go back to results. Now we want to plot. So direct plot, main for DC analysis that we are using, but the function we want to plot current versus voltage. So choose the current, and here it says select instance terminal on your schematic. So for this voltage source, the drain, we want to draw that, we want to plot that. Just click on this terminal of that, and you would see your ID current versus VD, which is from sweeping from 0 to 2 volts. And as you see, you would have one of these plots. For VGS is 1 volt. By sweeping the VDS from 0 to 2 volt, we have the ID. And the maximum of ID is 2.8 milliamp. Now the last goal of this simulation in the Cadence is we swept the VD from 0 volt to 2 volts, and we have one of these graphs. Now we want to see by changing the VDS, by increasing the VDS also from 0 to 2 volt, different VGS, what happens to these graphs? Would we get the higher current or not? The next step is to vary the VG. For that, we need to go to this tools bar, parameter analysis, and here add the variable, add the VG. Again, we want to sweep from 0 volt to 2 volt. Choose the linear steps, and put like 0.5 volt. It will do 0, 0.5, 1, 1.5, and 2. It will do 5 simulations. Just run. And again, go back to results. And the current. Let me change the color of this to be more visible. And you can come to the style and make it solid instead of that. So this is the plots that we were looking for. Still ID, the current of the transistor, milliamp, versus VD, 0 volt to 2 volts, for different VGS. VG is, you see VG is 0 volt, is the yellow one. You see the current is around like picoamp, transistor is off. When VG is 0.5, very close to threshold voltage, still transistor is in the area to turn on, but still the current is very low. It's like 75 microamp. And when the green one, when your VG is 1 volt, VG is higher than threshold voltage 0.5. 1 is higher than 0.5. And your transistor now is on. And you will see the maximum 2.8 milliamp. And if you keep increasing the VG, you will have a higher current. By ID is a direct proportional with VGS. If you increase the VG, you would have a higher VD. VG 1.5, the maximum current would be 6.6 milliamp. And if the VG is 2 volt, the maximum current would be 10.2 milliamp. So our goal was to plot a very simple circuit for our NMOS transistor and plot the IV characteristics of this NMOS transistor with the different VDS and different VGS. This is the end of this session, and thank you so much for participating in this class, and have a good day.